Hi everyone. This is ME 6750 thermoelectric material. I'm sorry, I have a couple of late. It takes time for me to prepare uh, WebEx. Anyhow, today we're gonna move on and discuss important property, transport property. Okay. So electronic transport properties, okay, for electrons. Phonons, maybe next hour. So Seebeck and electrical conductivity and thermal conductivity of electron, something like that. So all electrons, okay. Uh, this is somewhat important. I'd like to a little bit discuss the fundamental. Electrons is moving, and there is atoms, all around. Um, Very complicated potential, sometimes moving and collide. Okay, so very complicated motion, and anyhow, yeah. So in order to describe um, the the electrons, we need to think about the function mathematically. It depend on the time and also distance and momentum usually. Okay. So time, distance, and momentum according to particles physics. So once three variable and mathematically differential forms, we can say that in terms of partial. A little bit we need yeah, directly. Okay, you might have question why, but that's the mathematics function partial r and dr, and the partial distribution is with respect to momentum and momentum difference. That's the straightforward, no question. It's math. Once we have three variable, we can say that. So we try to describe distribution in terms of equations. So divide by dt Um, this d is the total difference. Um, anyhow, if we divide, then partial the transient terms of respect to time, and uh, what is, I can little bit switch df again. The momentum is mass times velocity of a particle. So that here momentum, I can cancel the mass and the velocity. So this can be a dp. dp is df dv dv. I can say that. So and the r is arbitrary distance. So r the respect to the is this is the velocity, nothing more. So this is the velocity, and so dt divide dr dt, and just dr plus v df dv and dv. No, no. Rather than velocity, I'm sorry, a little bit. I can use p is momentum is a wave number over I think of 2 pi something. I think we have derived momentum. Let me check. No, p is hk. Sorry, I like to remind you. P is k over h bar. So Planck constant. So which means momentum in terms of wave number. So the f dp dp. I'm changing this. Is the f dp is k. The k h is eliminated, and the k in terms of k. So here, rather than v, I can use k. Okay, k and k No, dk dt, dk dt. So again, I can write um, dr dt is r dot, and df dr plus dk dt is k dot. Okay. So we come up with in terms of wave number. We're gonna use wave number. Uh, that's the equations 691, I think. Yeah, you can the book 691. Okay, so this is a straightforward. Actually, I just transform using the definition. So the if electron is moving, and this must be a distribution, and uh, it turns out not easy. Yes, we can do, but some numerical approach, they call initial, uh, ini, initial, or Monte Carlo, something. There are techniques, numerical, uh, but that's a very another field. We like to approach analytical. Okay, so this is so complicated. Um, the what the uh, total difference derivative dfdt, it's a kind of assumption now that people try to assume this is partial dt and collision. The meaning is collision. Okay, so well, actually, electrons moving and then collide and scattered. That's the we want to figure out. So we define this is collision, and then um, well, look at that. The f the t is changed with respect to time, is a transient, and the r dot is a velocity, and dr, and k dot, the rate change of wave number, and the k. Okay, with respect to k. Again, according to relaxation now, the difficulty relaxation uh, time approximation. You can look at the book RTA. RTA. Okay, so according to RTA is the collision is um, the in function disturbed, and undisturbed, and time. Okay, so that's the approximation. Is disturbed, undisturbed, time scattering practically. So we gonna solve this. Okay. Now, what we have to figure out is these terms. Okay, and this is something transient, so that we assume steady state. So this is zero. Okay, we just assume no stored energy, everything is conserved momentum. So now we look at this and this. Okay, so the um, we look at the first the the rate change of wave number and the k. We like to figure out this in terms of yeah. So that now um, the force is F equal ma. A is velocity respect to time. Between the particle is turns out the electric field. Okay, if there is electric field, Coulomb forces. This is always. So it turns out like that. Okay, now so this is because MB, um, I told you we have a P is MB is HK. I told you that according to Bohr's yeah model, Bohr's model. So you remember this, and then MdV is this. Now is nothing more than H um, um, dk dt. Look at that. So k dk dt is like same as this. So that we like to develop k. This is dk dt, and the f dk is um, dk dt is It turns out in we are using dkdt, it is um, yeah, minus h electron electric field df de. Okay, no, dk. So we can come up with this, and the E energy we like to express in terms of energy. The K is we have expression energy of particle is h k square. I think you remember m, and what was 2m. Yeah. So 2m m square v square. So this is momentum h square k square 2m. Yeah, 2m. Something like that. So dk is, I can derivative 2 kh square 2m. M2 is, so energy with respect to wave number, we have some expression. So that finally, I think you did some homework, but K df dk is minus electron charge, and uh, I'm gonna distinguish. This is energy, and then electric field. I'm sorry, electric field is. I'm gonna use to distinguish energy. Okay, something like that. So that electric field and the velocity and df de. Okay, something like that. So anyhow, then the problem we need to figure out this one also. Okay, this was a little bit yeah. What is um, what is r dot df. We have to figure out this. Okay, so this is the same as a velocity now in terms rather than r. The f, the we can change to x for convenience. So r is a x, r dot is a v. We can do that. Okay, x, because we like to look at simplest one-dimensional analysis. Okay, we can go 3D, but one-dimensional. So we use X and V, and so this is um, we like to extend the respect to temperature, uh, and also I think you remember this distribution is the function of uh, let me see, energy, Fermi energy divided by kBT, um, something like that. It's a related energy, Fermi energy, according to I think you remember exponent energy, Fermi energy distribution, kVt minus 1, something like that. So let's say we introduce phi is energy uh, divided by kBt reasonably. Okay, we like to introduce because this is functional. So V is the F, the phi now, and the phi dt, the t dx. It's really, we need to expand because of we have to consider functional. So we look at that, and I'm gonna skip. You can the homework. We come up with uh, v function of the x. Yeah. So once we have that, and phi, I think we use phi d e is, if you look at expression, this is constant energy, and it turns out kVt. So using this information, um, df dx is df d phi d phi de and dt de. So we can defeat that's the kVt, and the f, the e, kVt, the Fermi energy respect to temperature, Fermi energy divided by kVt Boltzmann, and square. Um, and dt dx is a gradient. temperature gradient. So that is turns out minus dt minus E Fermi energy and the temperature, you know, and dt dx. So that now using the information we assumption between the scattering, this is a disturbed, this is a equilibrium, non-disturbed. That's what we assumed. And then this is time between collision. It turns out yes. So so that this is an external force, external electric field, and then Fermi energy gradient. This is so interesting. And then energy difference divided by temperature, and then temperature gradient. So that when we look at, we can rewrite is minus eliminate electric electric field external plus now minus and Fermi energy gradient and Fermi energy difference and gradient. This is so important relationship. We got it. It gotta be related. Something scattering, disturbed, undisturbed between collision. That's a related velocity of electron and distribution function respect to energy and something. So again, this relationship is a Boltzmann equation. Uh, yeah, Yeah, it's a well-known Boltzmann equation, but still, they the this disturbance, disturbed, undisturbed. The problem is, we want to figure out disturbed, okay? Because the undisturbed, it's a Fermi direct distribution. We know that. This is we know that, and then maybe, yeah, we can write, and velocity, and relaxation time, and energy, external energy, Fermi energy gradient plus energy divided by temperature dt dx. We can say that. But it turns out it's mostly this is no contribution. So and this is very close to, so they use velocity and the relaxation time rather than f. We use undisturbed approximation, but it turns out to be a very good. So this is finally they used to predict disturbed functions. Finally, we call Boltzmann transfer equation. Very famous. So you should know that Boltzmann transfer equation. So we have disturbed, undisturbed functions, and then we can maybe figure out. Okay, although there is some assumptions, we made it, but eventually we're going to use this relationship after collision electrons. Okay. Any question? But from this very important, we know that the temperature gradient is associated with electric field. That's we earlier. But interesting is these terms. So even this general electric field, general electric field uh, is general electric field external. I think external, I can use a little block. External plus 1 over electron Fermi energy gradient. So that's the electric field. So important we figure out. So if there is no external electric field, then electric field is nothing more than 1 over charge This is so important. We got it, electric field with a 699. So this analytical analysis indicate Fermi energy gradient is associated with the electric field internally. Okay, this is external. So this allow us, we can look at Seebeck coefficient. You know why? Um, um, because a general electric field is electrical conductivity and current density. This is Ohm's law. And Seebeck, this is kind of voltage. And gradient, temperature. We know that temperature, it creates the voltage. Okay. So that's the thermoelectric electric field, and then the what is nature of Seebeck? Nature of Seebeck is so difficult to figure out. If current is zero, if current is zero, then Seebeck is gradient electric field. That's the come up with it. So what is electric field? Is turns out internally 1 over Fermi energy gradient over dt, if it is a one dimensional gradient. Wow. This is Seebeck. We had some difficulty figure out what is the nature of Seebeck. Is turns out this now. Okay. So we'll figure out later, but this is basic Seebeck coefficient. You can raise a question. Students, are there? It's very quiet. Are you there, students?
Yep. Yes, sir.
Yeah, Tony. I know this might be a little hard for you, but you have books, you have homeworks. Now, more or less, you have to understand. Okay, that's the key essence of analysis. Okay. Now, again, when we look at it, what is a current? What is current is electric field and electrical conductivity. So what is electrical conductivity, is electric field, and the current density again. if gradient is zero. This is a special case. So electrical conductivity everywhere, even with a gradient, without gradient, this is a nature of. So once we figure out current divided by electric field, that's the electrical conductivity. So we will figure out the electrical conductivity and the Seebeck coefficient, okay, today. And also KE. We're going to figure out KE later. So, but the K over L is next week. Next week. This is electronic thermal conductivity. Lattice thermal conductivity is very important. I need several hours to discuss this. But today we will discuss thermoelectric transport property one by one. Okay? So let's look at the electrical current density is something is associated with the charge, but inverse of direction, you know that current is the inverse direction of electron, and number of concentration and the x velocity, because there's a number of velocity, but the x directional velocity. So this is the current. This is the current. So what is a N? I think what we define the electron concentration. I like to go back earlier work. Yeah, I started integration from 0 to infinity and density of state in terms of energy, density of state. And then we set the distribution, Fermi energy distribution in terms of energy. That's the density of state. Okay. So this is we defined earlier. I think you have to go and look at it. 2 pi square 2 m d star, effective material property, divided by h bar square and 3 over 2. And energy this is what we got density of state in general, so we can plug in and then uh, we this is a little complicated, but we look at uh, equilibrium undisturbed. Okay, so we look at the undisturbed first of all. So that n is disturbed is later, so that we can find 2 pi square, because this is constant, to m star d h bar square to an integral from 0 to infinity energy 1/2 an exponent e ef over k BBT minus, I'm sorry, plus 1. Plus 1. That was a Fermi direct distribution dE. So this is kind of a one-dimensional general, and um, well, I think in here this is assuming one valley conduction energy, valence conduction band, and something like that, the valence band, conduction band. But there could be more than one. So valley, number of valley. So we said the MB is number of valleys. It can be 1, 2, 3, depend on. So sometimes they put the NV, number of more than one, the number of electrons. Okay. Okay. Now, so what is here again? N E velocity. So again, we can look at the electron density minus plus um, the integral of electric charge, velocity, and density of state, and Fermi distribution. Okay, something like that. What is the density of state? The density of state is very important. So it turns out energy is power. So something like that, according to one-dimensional analysis. And then the Fermi energy. This is Fermi energy, and then the Fermi energy distribution. So number of electrons, something. So what is the exactly density of state and then electron concentration? It's not easy to understand, but for easy understanding, I used to say electron or holes are people. Imagine density of states are house, so people can stay in the house. If there is no density of no house, people cannot stay. That's the something like that. So that is the density of state house. Okay, and then electron is people. So we like to have as many as houses so that the electron can stay. It depends on the, okay, so we'll see. And then plug in and we can move on. Um, because I can look at it, electrons, uh, x direction, velocity is g over e now. I can plug in, we found it, g over e. So I can look at it. Um, so the velocity and it turns out, including this, relaxation time, and yeah, G of E F distribution. Now I can use Boltzmann transport equation. Okay, just write down. Temperature gradient, dE. And then also I can plug in the density of state. So a little complicated, but the constant is put outside. Um, that's the current. Okay. Um, so once we have that, what is electrical conductivity is J over electric field. So that they over electric field 1e Fermi energy gradient. So some you can look at it, and it turns out um, this M is density of state. Hmm, interesting. Let's say this is for a moment its function, and then um, so that I can say that uh, this is energy and dFO dE, if I say that. So this is often used, and some our ancestors have some analysis. Um, N is a number of derivative Fermi energy, something like that. So that this is a second derivative, or higher order, second, third, fourth, fifth. So that usually higher order is negligible, we assume, if it is if the is much greater than 1. This is for metal. So in case of metals, we can neglect the higher orders. Um, So that if you look at it, if you look carefully, this is it. This is negligible, higher order assuming. And then if you look at that is this. So if we the this conclusion is, if you look at carefully, because it is defined like that, 2m. Um, it's approximately we come up with this. This is 111. That's what. So this is approximation anyhow. Okay, if it is metal. So it's interesting. Um, Gold. Do you think you remember you can find Fermi energy? Yes or no? Answer. No one remember? If you remember, say yes. Then do we have to go back and Fermi energy for gold? No one? Okay, so we can go back. Um, let's go back. Okay, I think we discussed example 6.5, pyramids in gold example, and assuming FCC, so that we can figure out the number of, assuming every atoms provide one electron, because valence number is gold is 1. That's why we know number of valence electron for any element for gold is 1. So if it is 1, then the lattice point, there are 4 FCC atoms. So total number of electrons we figure out. Once we have total number of electrons, um, according to if we have a total number of electron, and then we can figure out the Fermi energy for metal in this case. Okay, so we did it. And Fermi energy is N is plug in this. We got the 5.52 electron volt Fermi energy. Okay, so we have it. 5.52. Oh. So now look at it. This is a 5.52 electron volt. And M is a Fermi, no, density of state. Density of state, density of state, effective mass. So density of state, effective mass is comparative electron. So usually experimentally we can figure out, depend on the material, point A. So anyhow, so this is real. This is electron. So in terms of electron, we can, this is an experiment. Actually, we can figure out experiment. So suppose we know, or assume, we assume electron mass, same, whatever. So we have an electron mass. This is constant. All we need, this is a charge, and this is a electation time. So if we have electation time, we can compute electrical conductivity. If we have electrical conductivity, we can compute the electation time. Okay, assuming for metals. So yes, we know the goal, the Fermi energy, and then I think example here. Example here is, look at that. Electrical conductivity is given. So electrical conductivity is given, then we can compute electation time, 10 to the minus 14 second. I think we assume the M is just the electron mass, assumed. Yeah, assumed actually. Okay, now the property of metal, I posted this, you can have this, is experiment, copper, aluminum, silver, lithium, silicon, germanium, and here the ratio over electron is given. This is either experiment or computation. We can figure out. Okay, interesting. So that density of state, in terms of electron mass is known. And also, band gap is is you know this is band gap, uh, valence band, conduction band, and this is band gap measurement. So this is very important property. Um, Maybe either we can calculate or we have a measurement so that we can work on that. Um, okay, I'd like to have a break, about 10 minutes. I will be back. Okay, thank you. Bye. Hi, I'm back. Um, let me see. So this um, electrical conductivity is one of the important, the figure of merit, the Seebeck, electrical conductivity, and thermal conductivity. So it's important. Okay, Seebeck. So what is according to this, we can see that um, Fermi energy, near the Fermi energy, because energy is all distribution, but the Fermi, near the Fermi energy is important, turns out. Okay, so near the meaningful Fermi energy it turns out. Okay, um, so again, some um, energy and uh, this is density of state, Fermi energy, energy and distribution. So around the Fermi energy, that's the area of important for thermal conductivity and electrical conductivity, the meaning. Okay. So analysis is so important. Analysis. It gives us some information. Uh, okay. Now we'd like to look at uh, Seebeck coefficient. So that electric field is electric current and electrical conductivity and the relationship Seebeck and temperature gradient. So temperature gradient is associated with the electric field if there's no current, if there's no current. So Seebeck is nothing more than electric field divided by temperature. What is the electric field? I think we figure out Fermi energy again. Fermi uh, Fermi energy gradient and dt dx. So once you figure out these, um, yeah. Okay, now, so let's again look at the current density um, is we know that the inverse and integrate and we're using previous information And um, we can say that now using some previous information. So I said current is, when we discuss the CBEC, current is zero. So this is a zero, and then we like to look at these forms from these. So that using the relationship, um, and also again the second order neglecting it is a little, we need the work, but this is zero actually. Um, no. So using these two terms, um, we can figure out um, something like that. Natural law, electrical conductivity, derivative respect to, and this is CBEC according to. So, wow, this is a beautiful mode formula uh, is known. Okay, so we're able to have expression. Otherwise, it's very difficult to figure out. Um, so um, if we use some informations, um, I think I'm gonna skip, but you can come up with a different version of mod formula. uh, Pi square 3e kb square Boltzmann constant temperature and density of state and electron concentration and uh, the and mobility, but everything close to Fermi energy, another formula. This is very important. Um, so for the developer of a property, something we like to understand how we can have a good material for thermoelectric. Um, so in the later, I think I skipped, but there is relationship NE square and M. So we define NE mobility. So mobility is nothing more than electron and location time M. So this is Debye model, it turns out. So it turns out in terms of mobility, this is electron mobility important. Mu, electron mobility. Okay. So it's a very important property of electrons, it turns out. So, okay, now, so we look at this, Seebeck is proportional to density of state. which means as many as a house, as many as a house, good. Seabag is good. But the electron, it could be holes in type of p type. N type is electron. Is inversely proportional. So many electron does not help to have a high Seebeck coefficient. House is yes, but electron is less. Mobility is a little complicated, but I think since the n is e mu energy, this is nothing to I would say this is one over mobility density. I think ZE, another forms, this can be DZE DE. I think something we can develop rather than this mobility or in terms of. So what is meaning now? We can see more house, more density of state, good. Less electron, good. And then inverse, but this is a little complicated, but the gradient, this is very important. Density gradient high is good. Density gradient high is good. So I'd like to show you some computational result. This is germanium. This is germanium now. I think we have discussed this is a Brillouin zone of K-space, like that. So we understand is just 1 billion zone represent whole specimen. At the boundary is a boundary of a unit cell. But center is a very large. K is small. Is again K is 2 pi lambda wavelengths. So K small is a lambda wavelength is large. So it take care of entire specimen. So directional from center to X and L. I think X is L, X is here, L is here, something like that. This is boundary. Another K sigma. Yeah. Anyhow. Yeah. So usually this is germanium. It turns out this is Fermi energy. So to let's look at the germanium. Appendix D. Yes, germanium. This is germanium. So valence is 4s2. 4 is uh, quantum number 4, s2 p2. 4. Valence is 4, germanium. So that we understand, I think this is 2 and 2, 3 and 4. Anyhow, the 4 that there is valence band and conduction band, something like that. Okay, so this this is uh, what is the name of it? Anyone answer? The distance valence top and conduction bottom. Answer. Somebody answer. What's the name?
Band gap.
Band gap. Yes. Band gap. Band gap. Energy gap or band gap. So that's a band diagram, band structure indicate Fermi energy and valence band. How many? Here I look at two. The valence, I think at least two, three, because there is a two is separated, and there is another two. At least three, four, something like that. We can see that, and this is I believe what is a this is energy. So this is a valence band and this is conduction band. So the valence band and conduction band, the energy gap, this is energy gap. We understand this is real actually, rather than we just assume the parabolic, but the one side is a p type and then electron, yeah, conduction, something like that, and then the steeper the better. Do you see? That's what the steep density of state, steep is better, and then less electron is better, and house, more house is density of state is better. Something like that. We can have some from the theoretical. This is the again density of germanium. Germanium, the electron is between atoms of germanium. There is a very complicated potential and something like that. That's the I think this is about here. We can see this is numerical computation, more or less. So this is very important band diagram or band structure. Band structure, they call it. Okay, to analyze, we need band gap. First of all, we need the band gap. Without the band gap, no, we need the band gap. That's why N-type, P-type. So germanium might be a candidate, but what time is if you look at carefully, um, I think that this bottom conduction, this is something less than that. So this is look like indirect band gap, indirect, not the really. Thermoelectric is okay as long as indirect is fine for thermoelectric material, but the laser, no, laser need exact direct because momentum must be coincide. Otherwise, we have a difficulty to form the laser. So this is not the good. Germanium is no good for laser. So in order to find the laser, I think gallium arsenide, similar, very similar, gallium arsenide binary. Um, when we look at this is look like a direct. You see that bottom top is coincide k space. So this is good for laser material. Okay, also good for thermoelectric material. I think as long as there is a band gap, um, and then we can see how many valleys, 1, 2, 3, 4 valleys. This is very close, but also it might work as a band gap, very close energy. Okay, so uh, so we'll see the effect of that. Now, the according to measurement, I think you can find this one also. I posted. This is a CVEC. Uh, this is electrical conductivity. So, no, inverse resistivity is inverse actually, but anyhow, same as electrical conductivity. This is K. I think K of E, I believe, yeah, total or whatever. This is the thermal conductivity, depend on the temperature. So that we have a measurement and our theory is in agreement, something. That's the theory and measurement we have agreement. Now I'd like to look at a little bit more about so this is a CBEC we discussed, Mott formula we discussed, and some in terms of yeah, R and there are we'll discuss, but anyhow, so we can compute the gold as long as we have Fermi energy, we can compute using this. Okay, using this, we just a different version of alpha from Mott. Okay, so you can use it or use it, and you can compute CVEC. That's what. If we assume R is a minus, so that we can estimate for gold the CVEC is too small because this is electron, so it's minus. It turns out holes is a plus, so small. Now I think I have to look at the thermal conductivity of electronic thermal conductivity. K is consists of 2 Again, K is obviously thermal conductivity, heat flow, temperature gradient. Now, the heat flow is turns out uh, as long as the number of electron is moving, that has energy. It's quite simple. I think this is very important. As long as the electron is moving, that carries energy. So that we develop the same way, and then we found Lorentz number is a ratio of electronic thermal conductivity, electrical conductivity ratio is constant. That's the so weird. That's constant. The ratio is constant. Is Wiedemann-Franz law. All chemistry they have this material. So if it is constant, means more electron conductivity, electrical conductivity, there are more thermal conductivity. Very difficult to control. Anyhow, using the equation, we come up with this and then this. So interested, we come up with this is constant. Lorentz number is constant. Sigma is electrical conductivity, temperature, but minus Seebeck square sigma t. So higher Seebeck, we can reduce, although constant, we can reduce because Z is alpha square sigma K E plus KL. So reduce is better figure. This one we'll discuss later. Reduce. So it's good actually. Higher CVEC, then it can reduce. Okay, so this is so important. We learn from the equations analysis. I think you can look at the analysis now. The tau relaxation time is turns out time constant and related energy. That's the we uh, figure out. So that is a related energy, the relaxation time, and there are three. For acoustic phonon scattering, there are three type of scattering: ionized impurity scattering and polar optimal scattering. Different are numbers. This is a major minus, mostly. Minus half is acoustic phonon scattering. And also we assume the uh, isometric and the kinetic energy is nothing to do with it's only temperature dependent. So electrons kinetic energy, and since the same, nothing to do with the directional, this must be the same. It's very interesting. So that when we look at it, um, it's coming with another uh, effective mass. We have different mass name or inertia to the same conductivity, effective mass, or inertial effective m over c. M of d is a density of state. But now we have conductivity. We'll discuss more. It turns out because the velocity is same 3, and the x direction in terms of energy 2e over 3. So we use this for one directional. Okay. When you're using that, the R is depend on the scattering technique and density of state. We include his value, number value, density of state. So value of a number, more value is the better density of state, more house. So this one also important value number, and they're using some Fermi integral. This is many forms, and then we say Fs, and then S is depend on the numbers because of R, 3 R's, and we use CVEC now is in terms of R, the same, but in terms of R, and depend on the scattering material. Acoustic scattering is minus half, and there is the Fermi integral is, there is a table, you can look at it, table, appendix, then you can get the, you don't have to integrate, just a table. Once you have a half or something like that, you can get it. So you can compute actually using the appendix, and you can compute. I think that some of our homework you can do, you can compute even the Lorentz number. So when we look at it, CVEC is a plus minus, so absolute value, holes or, and the electrical conductivity and electronic thermal conductivity. Look at that. This is the result. This is actually, we use acoustic scattering assumption. R is a minus. So this is Fermi energy, reduced Fermi energy. The Fermi energy, reduced Fermi energy, I think Fermi energy kV T, I think, something reduced. So Fermi energy change, increase, decrease, is very interesting. The CVEC, if you decrease, CVEC is increase, but electrical is a decrease. And the electronic thermal conductivity decrease or increase, the vice versa. So this is nature of, that's one of the difficulty. We cannot just increase. One is increase, the other is decrease. So that we have a limitation. And the Lorentz number, reduced Fermi energy, I think depend on the scattering mechanism. 3 scattering button. No matter what, if the Fermi energy high, this is metal. Metal. If it is high Fermi energy, if it is metal, then it's constant. That's a Wiedemann-Franz law. But so metal is constant. Semiconductor is not constant. That's why we use a semiconductor for. Okay, look at that. Now we use these, and then we try to plot the GT and try to define the better is functional better. The others are all Fermi. So that the Fermi energy depend on the, and then depend on the better. better is this. So that the GT is depend on the better. Um, but it turns out the technology is about here. We have here. But it's possible. 3, 4, depend on the. So what is a more study of better? I think we will discuss more. It's very interesting. Very interesting. I will discuss later, next hours. I think the homework, there is no homework additional, but you can complete the homework so far. You can, we will accept the late homework. I think how much you, I'm not sure how you did work on homework. Oh, looks good. But I will, you can correct, okay? You can correct your homework. I will accept the late homework. I think you better check again your homework, okay? So no more additional homework, but next week I will grade the homework. Any question? I'm done. Thank you for your,
Oh, I was
yeah.
wondering when you were gonna cover like the midterm material, like what will be on the midterm.
Yeah, I think midterm so far, yeah, I think I'm going to cover.
Is the midterm next week or?
No, 27.
Oh, okay. 27th. The 27th is a Monday.
Oh,
I thought the class period right before spring break. I thought you said 22nd, which would have been next week. But
wait a minute, wait a minute. How come next week is midterm? No, I'm gonna change. The midterm is a 29. Okay, I'm gonna change
okay,
it.
so next week you'll cover what will be on it then.
Yeah, yeah, yes, yes. I'm
Okay,
sorry.
thank you.
Yeah, I'm gonna change one more week. I need to cover, yeah, the midterm. Okay. Bye bye.
Thank you.
Bye, thank you.
Bye bye.
Bye, Professor.
Bye.